Okay, so we've seen that for an aircraft in steady level flight, the airspeed at which the thrust required to maintain steady level flight is minimized can be written as, or is also known as the minimum drag airspeed, and can be written like this. Okay, and this is all assuming that the thrust angle is close to 0. So this is a very important airspeed, right? But then the question that might come up is, what happens if this assumption that the thrust angle is close to 0 is not true? And that's what we want to talk about now. So here we're going to talk about finding the minimum drag airspeed for non-small thrust angles. Or maybe this is better said, for alpha t is not approximately 0. It still might be small, but it's significant. Okay, it makes a difference. Okay, so in order to do this, let's go back and look at our aircraft in steady level flight with a non-zero thrust angle. Okay, so here's our airplane. Kind of a chunky little guy. And it's flying, we'll do some blue here, straight horizontal in steady level flight. And the forces on the airplane look something like this, okay? So again, the lift is straight up, the drag is straight back, parallel to the free stream. The weight is straight down, but now the thrust angle is going to be offset from the direction of flight just a little bit, okay? And this angle here is the thrust angle, alpha t. Okay, so that's just recap. Okay, so for this condition, again, we're going to review here. For this flight condition, we're going to have drag equals TR cos alpha t, and lift equals weight minus TR sine of alpha t. Okay, and the thrust required in review here, if you'll remember back, the thrust required is the weight divided by L over D cos alpha t plus sine of alpha t. All right. Okay, so if we look at the thrust required, we want to find out how to minimize the thrust required, right? Thrust is expensive, it uses fuel, so why not minimize it? Well, there's a few ways we can do this. One is to reduce the weight, but unfortunately the weight is often set by mission requirements. I mean, you can imagine for like a commercial aircraft, reducing weight is not that easy, especially because most of your extra weight beyond the weight of the aircraft is the weight of people, right? And we don't want to be jettisoning people during flight. So instead, if we want to minimize thrust required during flight, what we'd want to do then is maximize L over D. Okay. Now this is really convenient because L over D is a function of airspeed, and as a function of airspeed, L over D has a very nice maximum. So I'm just going to draw this real quick. So this is a look at what L over D looks like as a function of airspeed. Okay, so let's put on these axes here. This is your airspeed. This is your L over D. And generally L over D looks something like that. Okay, so there's a very nice maximum here at some specified velocity. And this is usually around, I don't know, 10 to 13 or something like that for most aircraft. There's some that have much higher, some that have lower, but this is kind of a good ballpark average. Okay, so what we need to find then is this airspeed. All right, Well, in order to do that, we'll start off by writing the lift to drag ratio. I'm going to change colors now, okay? Just to say that we're moving on to a new section. So now we're going to maximize. We want to maximize L over D, right? So that we can minimize thrust required. So maximize L over D. All right, so the way we do this is first we want to find an expression for L over D. And this is really easy to do because L over D, as the name implies, is just the lift divided by the drag. So we have L over D equals 1/2 rho v squared SW CL over 1/2 rho v squared SW CD. Okay, now real quick we can see that these cancel out, and so we're left with CL over CD, but recall that CD is a function of CL, so we can write it like this: CD naught plus CD naught L CL plus CL squared over pi ERA. So now we have the lift to drag ratio as a function of CL. But notice we don't have velocity explicitly in here anywhere. Okay, so the velocity is built into the lift coefficient, but it's not in here explicitly. So what we want to do then is, on the way to finding the velocity that maximizes L over D, we're going to find the lift coefficient that maximizes L over D. Okay, so the way we do that is we take the derivative of L over D with respect to the lift coefficient. All right. And that looks like this. Let's write this out here. Okay, so it's going to look like this. After some simplification, we end up with CD naught plus CD naught L CL plus CL squared over pi ERA. Okay, so we're just applying the quotient rule here. Minus CL times CD naught L plus 2CL over pi ERA. Okay, and I'm going to use the nice line here. It's a long line to draw. Over the denominator squared. Okay, so that's going to be CD naught plus CD naught L CL plus CL squared over pi ERA squared. All right, set all that equal to 0. And now what we want to do is solve for CL. Okay, but quickly we can see that in order for this to be 0, we just need the first term on the numerator to equal the second term in the numerator. So we can rewrite this as CD naught plus CD naught L CL plus CL squared over pi ERA equals CL CD naught L plus 2CL over pi ERA. Okay, so there's some terms that can cancel out, right? So this cancels with this because we have CL times CD naught L. And we get rid of this 2 here because we already have one here. So we would subtract this over, right? Of course, when we have CL squared over pi ERA. And what this all boils down to then is that CD naught equals CL squared over pi ERA. And we can solve that for CL to get that the lift coefficient at which the lift to drag ratio is maximized is equal to the square root of CD naught pi ERA. Okay, look at that. So we've found the lift coefficient at which the lift to drag ratio is maximized. But we're not done. So First, what we want to do then is now find out what the maximum lift to drag ratio is. So if we come back up here, we call lift to drag ratio CL over CD, which is a function of CL. And if we use this maximum L over D CL and plug it back in, we'll find maximum L over D. So that's going to look like this. So we're going to say L over D max then equals square root CD naught pi ERA divided by 2 CD naught plus CD naught L root CD naught pi ERA. Okay, now I did something tricky here. I want to just point out. Okay, remember that CL is root CD naught pi ERA, but that CD naught is equal to CL squared over pi ERA. So when I plugged this back in, I substituted this term here with CD naught to get 2 CD naught on the denominator. Okay, so there we have it. There's our L over D max. Okay, so we got two pieces here of a puzzle. All right, we have the lift to drag, the maximum lift to drag ratio, and we have the lift coefficient at which it occurs. Okay, so these are important things here, so I'm just going to star them. Okay, now recall, if we go all the way back, what we were trying to do. Let's just kind of get back in touch with what we were trying to do. Our goal here was to minimize the thrust required by figuring out the airspeed that we should travel to minimize the thrust required. And we found along the way that in order to do that, we want to maximize the lift to drag ratio. So the goal here is to find a velocity, and we don't have one. But remember that the lift coefficient is a function of velocity. So let's go back and revisit the definition of the lift coefficient. Okay. So for our scenario here, we have a function for the lift. So let's use that in our lift coefficient. So let's see, that's W minus TR sine of alpha T. Okay, so I'm just going to rewrite that here at the bottom. Let's see. Lift equals W minus, TR sine of alpha T. Okay? All right, so the lift coefficient then is just going to be CL equals lift divided by 1/2 rho V squared SW. And so that's just going to be W minus TR sine of alpha T over 1/2 rho V squared SW. Okay? Now, we don't know what the thrust required is right now, right? We're trying to find the velocity at which the thrust required is minimized, okay? And that so happens at this lift coefficient. Okay, so we don't know what it is, so let's put in what we do know about the thrust required. Okay, so remember, I'm going to scroll back up again. Sorry, I keep going back and forth. But the thrust required is W over L over D cos alpha T plus sine alpha T. So let's plug that in, okay? So our CL then, sorry, I want to scroll down just a little so we have our maximum lift over drag CL in there. Okay, so what we'll have then is W minus W divided by L over D cos alpha T plus sine alpha T, put all that in parentheses, all divided by 1/2 rho V squared SW. Okay, now we can simplify this. Oh, excuse me. This should also have a sine of alpha T here. We can simplify this, and I am not going to do all the steps here. So if you're really interested here, I encourage you to follow the steps yourself. But essentially we can simplify this entire thing to the following. CL equals W over 1/2 rho V squared SW times 1 divided by 1 plus D over L tangent of alpha t. Okay, so now here is an expression for the lift coefficient for an aircraft that does not have a nearly zero thrust angle. Okay, so let's consider the lift coefficient at which L over D is maximized. Okay, that's going to look something like this. Okay, so CL equals weight over 1/2 rho V squared SW times 1 over 1 plus, and so this is just going to be, right, 1 divided by L over D max, which we know, tangent of alpha t. And we know that this CL is equal to the CL we found up here, which is square root of CD naught pi ERA. All right, and so now we can find the velocity, right? All we have to do is solve this expression right here for the velocity. Okay, because we know L over D max, we can plug that in. So that's this right here. And we have CD naught pi ERA. Now again, I'm not going to go through all the steps. I just want to point out that this term, I'm going to do this like this. Okay, so this term here is blue star, right? So that's here. We can find that expression. And then this we've already plugged in. This was CL, right? This CL was a blue star, which gave us this term right here. Okay, so plugging L over D max in, we get our final answer here, which is V equals, and so this is after a lot of simplification. So again, if you're interested in this, I encourage you to go back and really work through all this. But it's going to come out to look like this. Square root of 2 over the fourth root. Well, let me make sure I get this right here so that we're not messing you up. Fourth root of pi E RA CD naught, that is a 4, times square root of W over SW divided by rho. So again, here we have the wing loading. Okay, now this last term is, let's see if I can write this cleanly. It's kind of an ugly thing. So this is 1 divided by a whole bunch of stuff, okay? 1 divided by 1 plus 2 square root of CD naught over pi ERA plus CD naught L all times tangent alpha t. That's in the bracket. Sorry, this extends there. Okay. And so this is the velocity at which the L over D is maximized and the thrust required is minimized for an aircraft with a non-zero thrust angle. So again, this is known as the minimum drag airspeed, just like it is with a small thrust angle. But the key here is that this, of course, is for alpha sub t not almost equal to 0. Okay, so really quickly, let's recap. Pardon that. Okay, so just really quickly, let's recap. We have, we went back and we have our expression for the thrust required. We found that in order to minimize the thrust required, we wanted to maximize the L over D. So we wrote an expression for L over d and found that it was a function of the lift coefficient, and it was not an explicit function of the velocity. So we decided to maximize L over d with the lift coefficient, and we found this lift coefficient here with the blue star. We plugged it back into the L over d and found the L over d max. Now something to point out, and I didn't point this out earlier, but notice that the L over d max is not a function of the airspeed. It is only a function of the design of the aircraft. So CD naught is a fixed parameter for an aircraft. Aspect ratio is fixed. Oswald efficiency factor is fixed. All of these things are fixed design parameters. So for an aircraft, the L over D max is a single value regardless of the airspeed that you're flying at, or the flight condition. Okay? Anyway, we found the L over D max and the lift coefficient at which it occurs. From there, we use the definition of the lift coefficient and the thrust required to find an expression for the lift coefficient as a function of velocity and L over D. And we noted that L over D max occurs at a specific lift coefficient. And so from there, we could solve for the velocity at which L over D max occurs. And finally, we came up with our minimum drag airspeed. So here we are. And again, this is for thrust angle not close to 0.